Welcome to the session. In this session, we are going to discuss about the first shifting theorem. So in our previous session, I just uh, give a brief introduction of the first shifting theorem. So let's discuss some additional examples related to this first shifting theorem in today's session. So let's start from the way of stating theorem. So here we can state the theorem as if we have a function f of t has the Laplace transform capital F of s. Then we can find the Laplace transform of the new function e to the power at times f of t, and the new Laplace transform is f of s minus a. So that means, so if we summarize this, let's say we have a function, f of t, and if we consider the Laplace transform of this function f of t, it is equals to capital F of s. And then if we multiply this function f of t by e to the power at. So if we consider this as a new function, and if we consider the Laplace transform of this new function, it is equals to f of s minus a. So here this capital F is the same function as in the earlier case. The only difference here is we have to change the variable s by s minus a. So let's consider an example. So we know that when f of t is equals to, let's see, cos omega t. When f of t is equals to cosine omega t, then the Laplace transform of f of t, it is equals to s over s squared plus omega squared. So if we multiply, if we consider the new function e to the power at times f of t, that means, let's see, it as e to the power at times cosine omega t. Then the Laplace transform of this new function e to the power at times cosine omega t, we can obtain it by replacing all the s terms in this expression by s minus a. So we can obtain the Laplace transform of e to the power at times cos omega t as, we have to replace s by s minus a. So s minus a over s minus a to the power 2 plus omega square. With that, we can obtain the Laplace transform of e to the power at times cosine omega t. So this is the process that we are using when we are applying the first shifting theorem. So if you are asking to state the first shifting theorem, you need to express it as if f of t has the Laplace transform of the function f of t is capital F of s, then the Laplace transform of e to the power at f of t is equals to capital F of s minus a. So this is the way of stating theorem. And if we consider the inverse Laplace transform, if we consider the inverse of the both sides, then we can say that the inverse Laplace transform of capital F of s minus a is equals to e to the power at times f of t. So this is the theory related to the first shifting theorem. And now we are going to use this theorem to do some set of example. So let's consider this example, example number 7. So you are asking to find the Laplace transform of e to the power at cos omega t and Laplace transform of e to the power at sin omega t. So let's start with this first. Okay. So we are asking to find the Laplace transform of e to the power at cos omega t. So before that, let's first we have to find the Laplace transform of cos omega t. And we can obtain the answer by just looking the table. So the answer is s over s squared plus omega squared. Similarly, we can find the Laplace transform of sine t also by just looking the table. So it is sine omega t. This should be sine omega t. Omega over s squared plus omega squared. And then, but in the question, you are asking to find the Laplace transform of e to the power at cos omega t. So if we multiply our function by e to the power at means we have to replace the Laplace transform of that respective function by we have to replace s in the Laplace transform of the respective function by s minus a. So we can obtain the answer as we have to replace s by s minus a in both numerator and the denominator. So we can obtain the Laplace transform of e to the power at cos omega t in this way, and the Laplace transform of e to the power at sin omega t as by replacing s by s minus a. Since in this function there is a s term in only in the denominator, so we have to replace that s. So this is the way of obtaining the Laplace transform of e to the power at cos omega t and e to the power at sin omega t. And then as the next part, we are asking to find the by using those formula. By using these two formula, we are asking to uh, find the inverse of the given inverse transform of this given function. So let's see how to do such a problem. So I will rewrite the problem. If we label this as capital F of S, this is equals to 3s minus 137 over s squared plus 2s plus 401. So if we have such a problem, and we can see that in the numerator there is a linear function, and the denominator we have s squared plus 2s plus 401. So by just looking this expression, we can see that we cannot see a pattern just like s squared plus omega squared, because there is additional 2s term were there. So if this type of quadratic polynomial is appeared in the denominator, the thing that we are going to do is we have to convert this entire expression into s minus a squared plus omega squared form. So let's see how to convert this type of quadratic polynomial in this form. So we call this technique, converting such a polynomial into this form, we call that this technique as completing perfect square. Completing perfect square method. So you have learned this thing in your O-levels as well. The Sinhala word is Varga Purnaya. So we are going to review your memory related with this thing. So I will explain this first by using a general expression. So let's see, we are starting from such a polynomial of the form ax squared plus bx plus c. So we are going to complete the perfect square of this type of polynomial. So the first thing that you need to do is As the first step, you have to check the coefficient of the x squared. That means the highest the term. If it is s, then s squared. So you have to check the coefficient of x squared. So if it is 1, if it is not equal to 1, then take it out as a common factor. So if the coefficient of x squared is not equals to 1, then you have to take it out as a common factor. If not, if it is equals to 1, and the second condition, this is the first. And if it is 1, no need to change. So if it is 1, we can proceed it as it is. So let's see the first case. In this, by just looking this polynomial, we can see that the coefficient of x squared, is equals to a. So then we have to take this a out as a common factor. So if we take this a out as a common factor, so then the coefficient of x squared is 1. The remaining coefficient of x squared is 1. And then, so if we take a out, then the remaining part is x squared. And then from this b, if we take b out, then the remaining one is b over a. That means if we taking b out here, that means we are multiplying this by, if we are taking a out here, that means we are multiplying a. And if we multiply by a, then we have to divide by a. So the remaining is b over a, x. And then here again we are taking a out. So the remaining is c over a. So this is the first step if the coefficient is a. The coefficient of x squared is a. So, and the second step, then as the second step, we are keeping this a as it is, and we consider, we are open a parenthesis, and we are writing the term, the variable here, by skipping this square term. We just write x as it is, and then this sign. So if it is plus, we have to keep it as plus. If it is minus, then it is minus. Plus. Since it is plus, so we have to keep it as this way. And then the coefficient of x, it is b over a. And then we have to write this is b over a. But we have to divide this by 2. We have to divide this coefficient by 2. So then the remaining term is b over 2a. So once we have obtained this one, we have to close bracket and square. So then from this entire expression, we need to reduce the square of this term, square of this entire term. So it is b squared over 2 to the power 2 is 4, a to the power 2 is a. And then we need to bring this c over 2 as it is. So once you have simplified this entire thing, you can obtain the answer for the complete imperfect square. So by using this technique, you can solve such problem. So let's move back with our example. So our problem is f of s is given as 3s minus 137 over s squared plus 2s plus 401. So here we can see that the term in the denominator is appeared as a quadratic polynomial. So if we complete the perfect square of this expression, then we can convert the term in the denominator in the form of s minus a squared plus omega squared. So this can be either s plus or minus. So we have to find that suitable way. So to do that, we have to consider the complete imperfect square. So this is the polynomial that we're going to consider. The polynomial that we're going to consider is s squared plus 2s plus 401. So here, first we are starting from the coefficient, and here we can see that the coefficient of s squared is 1. So we don't need to change anything. We can open a bracket and we have to write the variable only s. Then the sign as it is plus, and then we have to divide this coefficient of s. We have to divide this coefficient of s by 2. So if we divide 2 by 2, it is 1. And then close the bracket, square. And the next step, we need to reduce the square of this term. 1 to the power 2, and then this plus 401. So if we simplify this, we can see that s plus 1 to the power 2 minus 1 plus 401. And this is equals to s plus 1 to the power 2 minus 400. Sorry, not minus, it is plus. And we know that this 400 is plus 1 to the power 2, and we can rewrite this 400 as 20 to the power 2. So we have obtained this expression. We have converted this expression into the form of s minus a to the power squared plus omega squared. And here we can identify a is equals to, if s minus a, if we compare these two expressions, a is equals to minus 1 and omega is equals to 20. So once you have obtained this expression, we can replace the original problem, the denominator of the original problem, by this expression. So let's write, we can rewrite capital F of S is equals to 3s minus 137 over s plus 1 squared plus 20 to the power 2. And then we can rewrite the numerator. So since in the denominator there is s plus 1 term, so if we convert the term in the numerator is also into the s plus 1 terms, then we can use the expressions that we have obtained earlier. So to do that, we are going to expand this expression. So 3 times, if we replace s by s plus 1, if we replace s by s plus 1, then If we expand this one, this becomes 3s plus 3. And we have minus 137. But this 3 is something new that we have add. So if we add something into some expression, we need to reduce that thing. Otherwise, the equality of the equilibrium of the expression will change. So this minus 137 minus 3, this becomes minus 140. So we can obtain it in this way. And then now we can separate this into two cases as 3 times s plus 1 over s plus 1 to the power 2 plus 20 to the power 2 minus, so we can write this 140 as 7 times 20 over s plus 1 to the power 2 plus 20 to the power 2. So we are rewriting this 120 as, 140 as 7 times 20 is, if we are considering the structure of the sign, so the term in the numerator and this term should be equal. That is why we are rewriting this 140 as 7 times 20. So then we can obtain the inverse Laplace transform. So starting from this one, so we can keep this 3 as it is. So let's consider the inverse Laplace transform of both sides. Capital F of s. This is equals to, we can keep this 3 out. L inverse s plus 1 over s plus 1 to the power 2 plus 20 to the power 2 plus, minus 7 L inverse Laplace transform of 20 over s plus 1 to the power 2 plus 20 to the power 2. So we can take the inverse Laplace transforms. This is 3 times if we have s is over s squared plus 20 squared, then this is the Laplace transform of cos 20t. But here in this case we have replaced each s in the above statement by, we have replaced s by s plus 1. So if we replace s by s minus a, then we need to multiply the function by e to the power at. We have to multiply the function by e to the power at. But here we have replaced s by s plus 1. So the value of a is equals to minus 1 here. So we need to multiply our answer. If we consider this as s only, our answer is cos 20t. But here it is appeared as s plus 1. So we have to replace s by s plus 1. That means our value of a is equals to minus 1. That means we have to multiply this by minus e to the power minus 1t. So the answer is 3 e to the power minus t cos 20t and minus so if we consider this side, we can see that if we have 20 over s squared plus 20 squared, then the Laplace transform, the respective inverse Laplace transform is sine 20t. But here we have replaced s by s plus 1. So that means we have to multiply this expression also by e to the power minus at. So we can obtain, we can keep minus 7 as it is, e to the power minus t sine 20t. And this is the answer for that question. And then there are few more, there are another 3 examples. So let's go through with those examples as well. So here in this first two example, the term in the denominator is s squared plus 4s plus 5. So the first thing that we need to do is we need to complete the perfect square. So starting from the first term, we can see that the coefficient is 1. So we can just no need to change anything. We can start with this as it is. S, the first term is s plus, then the second term is 4 over 2. 2 to the power 2, and then we have to reduce the square of the second term. 2 to the power 2 plus 5, and we know that 2 to the power 2 is 4. Then we can obtain this as s to the s plus 2 to the power 2 plus 1 when we complete the perfect square of this function, this polynomial. So let's see how to obtain the answer for the example number 8. So here, part A. In part A, capital F of s is given as 2 over s squared plus 4s plus 5. And here, as we have, the first thing we have to do is we have to complete the perfect square. See, since I have done it earlier, I will just write it here. And then by just looking this one, if we have a function of the form 2 over s squared plus 1, so then we can rewrite this as 2 times 1 over s squared plus 1 squared. So that means this is of the form 2 times, this is something like sine, and if we compare this with omega over s squared plus omega squared, we can see that value of omega is 1. So this is 2 sine t. This is 2 sine t. But in our problem, this s is replaced by, in this example, s is replaced by s plus 2. That means s is replaced by s plus 2. If s is replaced by s minus a, then we will multiply the function f of t by e to the power at. So here we have replaced s by s plus 2. So here the value of a is minus 2. That means we need to multiply our function f of t by e to the power minus 2t. So with that we can obtain the answer as L inverse capital L inverse capital F of s. This is equals to e to the power minus 2t sine t. And since there is 2 term there, we need to keep that 2 as well. So this is the answer for the first part of this question. In the second part, the numerator is only changed, the denominator is same. So we can write the question capital F of s is s plus 2 over s squared plus 4s plus 5. So here also the first thing that we need to do is we need to complete the perfect square of the denominator. Since I have already done it, I am not going to do it again. S plus 2 over s plus 2 to the power 2 plus 1. And here we can see that in both, if if we have a function of the form this way, we know that the respective inverse Laplace transform is cosine omega t, but here omega is 1, so it is cos t. But here we have replaced this s, this both s by this s plus 2. So that means we replace s by s plus 2. If we replace s by s minus a, then we need to multiply the function by e to the power at. So if we compare this with this, our value of a is minus 2. That means we need to multiply the function by e to the power minus 2t. So the answer, the inverse Laplace transform of capital F of s is equals to e to the power minus 2t cosine 2t. Not 2t, cosine t. This is the answer. In the third part, the denominator is changed. So it is s squared plus 4s plus 3. So here also we can start from s plus sign as it is, divide 4 by 2, 2 squared minus 2 to the power 2 plus 3. So this provide s plus 2 to the power 2 minus 1, because this is minus 4 plus 3, it is minus 1. So the part 3, part C, capital F of s is equals to 2 over s squared plus 4s plus 3. So if we complete the perfect square, we can see that s plus 2 to the power 2 minus 1. And we can rewrite this as 2 times 1 over s plus 2 to the power 2 minus 1. So if this is appeared as, if some function appeared as omega over s squared plus s squared minus omega squared, the respective inverse Laplace transform is shin omega t. And if we compare these two results by just considering this as s, we can see that the value of omega is 1. So then the answer should be 2 shin t. 2 shin t. But in this problem, we can see that s is replaced by s plus 2. So if s is replaced by s minus a, then we have to multiply the function by e to the power at, but here s is replaced by s plus 2, then we have to multiply this by e to the power minus 2t. So this is the answer for that question. And then I have added some additional examples. So in the first example, we can see that the first one, we can see that the capital F of s is given as 1 over s times s squared plus 2s plus 3. And here, if we just look at this function capital F of s, we cannot see that such a function in our table. So if we complete the perfect square, even we cannot identify this type of function in our table. So if this type of function were there, the first thing that you need to do is you need to find the partial fractions and then apply the theory that we have learned so far. So let's see how to find the partial fractions of this one first. So this is the function that we are going to consider. And if we can see that this is a product of two linear ex linear and quadratic expression. The first one is a linear expression and the second one is a quadratic expression. So we can write the expression to find the partial fractions in this way. Bs plus c over s squared plus 2s plus 3. So once we have simplified this expression and find the constant coefficients, we can obtain a is equals to 1/3, b is equals to minus 1/3, and c is equals to minus 2/3. So once you have obtained these answers, you can write your expression capital F of s is equals to 1 over 3s minus 1 over 3 times 1 over 3 times our b is equals to 1 is plus 2 over is plus 1 to the power 2 plus 2. And then this is equals to, we can keep this 3s as it is, minus 1/3. We can rewrite this s plus 2 as s plus 1 plus 1. So we can separate this into two cases, s plus 1 over s plus 1 to the power 2 plus 2 plus 1 over s plus 1 to the power 2 plus 2. And then once we have obtained this one, we can write the expression to obtain the inverse Laplace transform. Inverse of capital F of s, this is equals to, if it is 1 over s, then the respective function is 1. But here we have 1 over 3s. So that means the inverse is 1 over 3 and minus 1 over 3 times. Here, if it is only s over s squared plus 2, so we can rewrite this 2 as square root of 2 to the power 2. So we can see that this is cos square root of 2t, but since here s is replaced by s plus 1, we have to multiply this by e to the power minus t plus here e to the power minus t sine square root of 2t, but since this square root of 2t, if we add the square root of 2t here, then we have to divide by square root of 2t, and that means we have lose. We need to multiply this by 1 over square root of 2. So with that, we can obtain the answer for the first question. And the second one. In the second one, capital F of s is given as 1 over s plus 3. S plus 3 to the power 3. So, if such a function is there, first you have to check whether are there any function of the form 1 over s to the power 3. So, without considering this part, just check such a function 1 over s to the power 3 is in our table or not. So, we have in our table a function of 2 factorial of s to the power 3. So, then we can see that if this is s to the power 3, then the respective Laplace transform is t to the power 2. So then we can just write it as, if this is 1 over s over 3, sorry, 2 factorial over s over 3, it is t to the power 2. And if it is only s over 3, then it is t factorial, 2 to the power 2 over 1 over 2 factorial. 1 over 2 factorial is equals to 2. So that means this is half t to the power 2. So we can write this as half t to the power 2. But here we have replaced s by s plus 3. So that means we have to multiply this by e to the power minus 3t. So this is the answer for the second one. So as for the third example, you are asking to find the Laplace transform of inverse Laplace transform of capital F of s over s squared minus 6s plus 10. So here also first you need to complete the perfect square, as s is equals to s minus 3 to the power 2 minus 9 plus 10. So this is equals to s over s minus 3 to the power 2 plus 1. And then we can rewrite s as s by s minus 3. Since we are reducing 3, we need to add 3 as well. In the denominator, s minus 3 to the power 2 plus 1. And we can separate this into two cases, as s minus 3 over s minus 3 to the power 2 plus 1 plus 3 over s minus 3 to the power 2 plus 1. So by simplifying this one, you will obtain the answer as e to the power 3t cos t plus 3 e to the power 3t sin t. So with that, we can obtain the answer for that question as well. And then as the next topic, I'm going to discuss about the way of finding the Laplace transform of derivative. So here, let's see, if we have a function f of t and its derivative can be found. So then if the Laplace transform of the function f of t is capital F of s, then the Laplace transform of f dash t, that means the derivative of the function f of t, is equals to s capital Fs minus f of 0. So I will summarize it here. Let me add the page and do it. Okay, let's see. We have a function f of t, and the Laplace transform of capital F, simple f of t, the function is equals to capital F of s. And then we can find f dash t. F dash t means d over dt f of t, the derivative of the function f of t. So then we can find the Laplace transform of f dash t, the derivative of the function, by considering s times capital F of s minus f of 0. So here this s is the variable that we are going to consider, and this capital F of s comes from the Laplace transform of the function f of t, and this f of 0, this is also something new. This f of 0 is coming from this function, the f of t function, when t is equals to 0. So if we can find these two cases, then we can obtain the derivative of the Laplace transform. Similarly, if we need to find the second derivative, that means f double dash t, the second derivative, d over dt f dash t. එහෙමත් නැත්නම් the second derivative. So if we ask to find the Laplace transform of the second derivative, then we can use this expression s to the power 2 times capital F of s minus s times f of 0 minus f dash 0. So here also this capital F of s, this s is the variable that we are using here, and here we have s terms, and this capital F of s, this capital F of s which is come from the Laplace transform of the function f of t, and this simple f of 0, the function value of the function f of t when t is equals to 0, and then this f dash thing, that means this one which is coming from this one, the function derivative of the function when t is equals to 0. So once we have identified all those terms, we can obtain the Laplace transform of the second derivative as well. So this is a summary. Okay, you don't need to go through with this statement and this statement. So just familiar with this expression as well as this one. So because when we are solving the differential equation, you need to use these two cases. Okay, so in the examination, I will provide a formula sheet which is consist of the table of the transformation as well as those formulas. But you need to know how to apply those formulas. In the examination, I will provide these expressions, but you need to know what are the meanings of this expression and how to apply those terms in the examination. So let's consider this example. So in this example 9, you are asking to find the Laplace transform of cosine t using the fact that the Laplace transform of sine t is equals to s squared plus, sorry, 1 over s squared plus 1. So we know that if we consider f of t as sine t, then the derivative d over dt f of t. So if not, we can write this as f dash t. This is equals to cos t. So to find the Laplace transform of cos t, we can consider the Laplace transform of d over dt sin t. If not, and then this is f dash. So this is equals to s times Laplace transform of sin t minus the function f of 0. The function is sine, so it is sine 0. And s, the Laplace transform of sine t, it is equals to 1 over s squared plus 1, and sine 0 is equals to 0. So we can obtain the answer as s over s squared plus 1 as the Laplace transform of cosine t. Similarly, we can use this concept for some other examples as well. So the thing that you need to remember under this, the Laplace transform of derivative is the formula. We have a function f of t and its Laplace transform is capital F of s. Then the Laplace transform of f dash t, the derivative of the function f of t, this is equals to s capital F of s minus f of 0. And the second one, the Laplace transform of the second derivative of the function, this is equals to s squared capital F of s minus s f of 0 minus f dash 0. So by using those two, you need to remember, no, don't need to remember because I am providing those two expressions in the examination, but you need to know how to apply those two expressions when we are solving differential equations. So now we are going to go move to the most important topic of this chapter. So that means the method of solving differential equations using Laplace transform. So here you need to use the two expressions that we have learned earlier. This one, the Laplace transform of the first derivative and the Laplace transform of the second derivative. And you don't need to proceed with this general statement. Actually, we are only going to use these two expressions. You need to familiar with these two expressions. So let's see how to apply those type of how to apply these two expressions to find the to solve the differential equations. So here, in the process of solving differential equation, before moving to the process of solving differential equation, I need to explain something really important related to differential equation. So let me add few pages. Okay, so let's review our knowledge related with ordinary differential equation. Okay, so starting from a differential equation, let's start from dy over dt plus y is equals to 0. So we can rewrite this as y dash plus y is equals to 0. So if we have this type of equation, these two cases are similar. These two cases are same. So we can identify the highest order of the derivative of this type of this equation is first derivative. Here only we consider first derivative. So we can identify this as the first order ordinary differential equation. So I will move to the next page and write this type of example. Dx squared plus dy over dx plus y is equals to 0. So this is similar with the equation d double prime y prime y is equals to 0. So if we consider this equation, here we can see that we consider the second derivative as well. Since we are considering the second derivative, we call this as the second order ordinary differential equation. Let me go back with the earlier case. So these two cases, this first order and the second order, these are differential equations. Actually, we cannot obtain the exact answer for such ordinary differential equations by using Laplace transform. So to obtain the exact solution of such an ordinary differential equation, we need to consider some additional condition as well. So we call these additional condition as initial conditions. So the meaning of the initial condition is, since we are when we are discussing about the Laplace transform, we are dealing with time. So if we consider a timeline, the minimum value for the time is t is equals to 0. So since t cannot be negative, so the initial condition means the value of, so the initial condition means the value of each variable at this time t is equals to 0. So we have to consider the initial conditions. So initial conditions means the values of y and y dash when time t is equals to 0. So let's consider first order ordinary differential equation. So if we write y dash plus y is equals to 0, the same first order ordinary differential equation, comma, something like that. Y0 is equals to a. So that means the meaning of this statement is, when t is equals to 0, the y value of y is equals to a. When time t is equal to 0, the value of y is equals to a. So if we write an ordinary differential equation with this type of additional condition, so we call this additional condition as the initial condition, then this entire problem become an initial value problem. Initial value problem. So we use the problem. Initial value problem. So we use the abbreviation IVP to represent initial value problem. So the first order initial value problem means there in a first order ordinary differential equation, there should be one initial condition. The most important, this is really important. So if the ordinary differential is a differential equation is the first order differential equation, there is one initial condition. So let's move to the second order ordinary differential equation. In the second order ordinary differential equation, as I mentioned earlier, here also we are going to define initial condition. So if we write this statement, that ordinary differential equation y is equal to 0, comma, y0 is equals to a and y dash 0 is equals to b. Then this become initial value problem. Here these two are, we can identify these two as the initial conditions. The meaning of each condition is this one: when t is equals to 0, y is equals to a, and here the meaning is when t is equals to 0, the value of y dash is b. Those are the initial conditions when we are considering the second order initial value problems. So we need to use these data to solve ordinary differential equation. Actually, we are going to solve initial value problems using Laplace transform. So let's see the first question. So we are going to solve the initial value problem. Y double prime plus y prime plus y is equal to 0 with the initial condition when t is equals to 0, y is equals to 0. When t is equals to 0, y dash is equals to 3. So let's see how to solve such problem. So earlier, when we are considering a function f of t, we have used the respective capital letter to represent its Laplace transform. So here, since we are using simple y of t, we are using capital Y of s to represent its Laplace transform. And here this y of t, the function of t, simple t, is the solution to the given initial value problem. So we are going to find this simple y of t. So starting from here, the first thing we need to define the variable, the function. So let's see, we are labeling starting from let capital Y of s is equals to the Laplace transform of simple y of t. And here this is for s greater than 0. So then we are defining the Laplace transform of capital Y of s. So once we have defining this thing, we are going to take the Laplace transform of both sides of this equation. So then we are going to take the Laplace transform of both sides of the differential equation. So our differential, I will write it here. Our differential equation is y double prime plus y prime plus y is equals to 0. So let's take Laplace transform of both sides. This is y double prime plus y prime plus y, and here Laplace transform of 0. And since we know that the Laplace transform is a linear function, we can separate these things by the addition sign of y, and this is Laplace transform of 0. So then we can go back with the expression. We can go back with those two expressions, the Laplace transform of f dash t and Laplace transform of f double dash t. So we know that the first one, the second derivative, the Laplace transform of the second derivative is s squared capital F of s. Since here we are using capital Y, we have to write it as y of s minus s y0 minus y dash 0. This is the first part. And then this one, we have to write the plus sign as it is. So the second one, the derivative, Laplace transform of the derivative, s times capital Y of s minus y0. Then again plus this one, the Laplace transform of y. It is capital Y of s, and this is equal to the Laplace transform of 0, and it is Laplace transform of 0. This is something new that you need to remember. This is equals to Laplace transform of 0 is equals to 0. And then once we have obtained this expression, we can substitute the initial condition. So the initial condition in this problem is when t is equal to 0, value of y is equal to 0, and t is equal to 0, y dash is equal to 3. So we can substitute those two values, y0 and y dash 0 by 0 and 3. So we know that y0 is 0 and y dash 0 is 3. Here y0 is 0 and here there is no y dash 0 term. And then we can obtain, since this part is 0, so here is squared ys minus this part is 0, s times 0 is 0, and this is minus 3 plus s times capital Y of s minus 0 plus capital Y of s is equals to 0. So once we have obtained this one, we have to subject this capital Y of s. So if we take common factor as ys out, it is plus 1 minus 3 is equals to 0. So if we subject capital Y of s, we can obtain 3 over s squared plus s plus 1. So once we have obtained this one, you have to find the inverse Laplace transform of the both sides of this equation. L inverse 3 over s squared plus s plus 1. And find the solution of this problem. Since we have discussed, no, since this is the first one, I will discuss the entire problem. So this is here, this is of the form as we discussed earlier. We need to complete the perfect square of the denominator. So let's consider this part separately. 3 over s plus 1. This is, we can keep 3 as it is. S plus the coefficient is 1. 1 over 2 is half squared minus half to the power 2 is 1 over 4 plus 1. This is equals to s over s plus half squared minus, no, plus 3 over 4. Oh, not in the numerator, it is 3, no, not s. And then we can rewrite this as 3 over s plus half to the power 2 plus square root of 3 over 2 to the power 2. So let's bring this 3 out. Let's bring this 3 out. And if in the numerator, if in our numerator there is square root of 3 over 2, then we can use the sign formula to obtain the answer. So in the numerator, by putting square root of 3 over 2 means we need to divide this by square root 3 over 2. So then we can write the answer. Square root 3 times 2 over square root of 3. And since this is of the form sine and omega is square root 3 over 2 t, and since s is replaced by s plus half, we have to multiply this by e to the power minus half t. So with that we can obtain our final answer as y of t is equals to 2 root 3 e to the power minus half t sine square root of 3 over 2 t. This is the final answer for the differential equation. So this is the structure of solving ordinary differential initial value problems using Laplace transform. So when you are solving any problem, you need to first explain the function, explain the terms, and then you need to take the Laplace transform of the both side of the differential equation. Then you can obtain this one, and this one. So when you are doing any example, please don't skip any step. Please proceed with all these step as it is. So from this step onward, your problem will be changed, because so if there are some coefficient in this problem, then the problem is changed, but you have to proceed with same steps. So then you can obtain the answer. So there is one more example. So I will quickly go through with that as well. So we are using capital Y of S as the Laplace transform of simple y of t, and then we are taking the Laplace transform of the both side of the differential equation. So then Ly dash double dash plus Ly dash plus Laplace transform of y. This is equals to Laplace transform of 0. So then we can substitute s squared capital Y of S minus s y0 minus y dash 0 plus s capital F of S minus, or not capital F of S, s capital Y of S minus y0 plus, for this one capital Y of S, this is equals to 0, and we need to substitute initial conditions. So when y is equals to, when t is equals to 0, y is equals to 2. So this goes to 2, and this is equals to 0, and this goes to 2. So we can obtain an expression s squared plus s plus 1 times capital Y of S. This is equals to 2s minus 2s plus, again here minus 2 is equals to 0. So you will obtain an expression for capital Y of S as 2s plus 2 over s squared plus s plus 1. So here find the inverse Laplace transform of both sides. So once we have obtained the expression for capital Y of S, we need to find the inverse Laplace transform of both sides of this expression to obtain the function y t, simple yt. So try to obtain the answer. I will just write the answer. So check whether you can obtain the correct answer or not. Of t cosine square root 3 over 2t plus two over square root of 3 e to the power minus half t sine square root of 3 over 2 t. So try to obtain this answer by yourself. And I will do one more example, since you most probably you will get such this type of examination problem in your exams. So here also first you need to define what is capital Y, and then take the Laplace transform of both sides. So the Laplace transform of y double prime plus the Laplace transform of y prime plus Laplace transform of y. This is equals to Laplace transform of earlier. For both cases earlier, the right hand side value is 0, but here it is 5. So then you can just write the expression for this one, and this one. And here, since the right hand side value is 5, the Laplace transform of 5. So if the function is 1, the respective Laplace transform is 1 over s. Since it is 5, it is 5 over s. So here we can write s squared ys minus sy0 minus y dash 0 plus s capital Y of S minus y0 plus capital Y of S. And here both initial conditions are 0. So this part goes to 0, this goes to 0, this goes to 0. So then you will obtain capital Y of S is equals Y of S times S squared plus S plus 1 is equals to 5 over S. And then capital Y of S is equals to 5 over S times S squared plus S plus 1. And here, since this is a product of two functions, the denominator is product of two functions, you need to find the partial fractions. S times S squared plus S plus 1, A over S plus BS plus C over S squared plus S plus 1, and then find the respective value for ABC. Once you find the value of ABC, you will obtain an expression for Y of S as 5 over S minus 5S plus 5 over S squared plus S plus 1. And then find the inverse Laplace transform in this capital Y of S, obtain the answer. So here also I will provide the answer and try to obtain it by yourself. 5 minus 5 e to the power minus t over 2 cos square root 3 over 2t minus 5 over root 3 e to the power minus t over 2 sine square root 3 over 2t. So once you have obtained, try to obtain this answer. This is the answer for this question. And complete the tutorial, and there are some additional questions in the tutorial as well. Please proceed with this example and practice well for the mid-semester examination. As I mentioned earlier, you will have the mid-semester examination on 28th February. So be practice with the set of examples for the exam, mid exam. Thank you.